Example 3.1.11. The generator in example 3.1.8 was found to have a line to neutral output voltage of 236.8 volts when operated at the rated current and power factor of 60 amps and 0.8 power factor lagging. If combined stray, friction, and windage losses are found to be 1.5 kilowatts and the core loss is 1 kilowatt, what's the efficiency of the generator when it's operating at the rated current and power factor? How much shaft torque must be applied by the prime mover at the full load, and how large is the induced counter torque? So the givens in this problem are we have a terminal voltage under load of 236.8 volts as a phase quantity. We know that the magnitude of the armature current is 60 amps. The power factor is 0.8. We know wasn't stated here, but in the previous problem, the synchronous reactance was given as 1 ohm. And this is a ideal generator coil, meaning it has no resistance, 0 ohms, or a negligible armature resistance. We were then told something about the stray, friction, and windage losses. So P stray plus P friction and windage is equal to 1.5 kilowatts. So two things have been lumped together. I'll explain that in a minute. And then P core is 1 kilowatt. We are asked to find the efficiency of the generator, the torque applied by the prime mover, and the torque induced by the armature reaction, or sometimes that's called the counter torque. So the solution, I want to start by drawing a power flow diagram for a generator. And so we've got some sort of input power that's going into the system from the mechanical prime mover. And there's always a relationship between rotational speed of a rotating body and the power that it has, and that relationship is defined as torque. So the torque that you apply via your prime mover times the mechanical angular rate of rotation gives you the input power. So let's draw that like this. So what's going to happen then is that input power is going to be converted into a rotation of the rotor, and there is going to be some loss mechanism. Inside the rotor, there's 3 loss mechanisms. The first we call stray loss. So a lot of times we say, there's some power loss to this stray loss right here. That first stray loss we call that stray loss. And stray loss is typically due to the magnetic field of the rotor not being able to, it's inconsistent, it's not perfectly shaped because it gets warped by the rotation. Basically, it's a fairly advanced topic. In this class, you just have to recognize that it exists, but it's basically not full magnetization by the rotor. So that takes a little bit of power out. Then what we've got is something called friction and winding loss. So this is the thing's spinning, so not all the torque gets converted into actual rotation. Sometimes the stuff, the rotor, the spinning creates some friction, so that's friction and windage loss. And I guess that reduces total power even more. Then what we've got is we've got another loss mechanism inside the rotor called core losses, and this is basically all the inability to totally create a magnetic field or loss in alignment of magnetic domains. So this is a loss in the magnetic core. And so those are the mechanisms of loss of converting input torque into a magnetic field that reaches the armature. So these are all the losses internal to the rotor, and we call this power converted. So this is the power converted from the input over to power converted over to the magnetic field that gets created in the armature right there. This is also the induced torque times times the mechanical rate of rotation. So this torque induced is the back torque created by the armature reaction. So remember the the magnetic field established in the armature then is responsible for the current flow in the armature. So there's one more mechanism of loss, and that is as current flows, that current can heat up the coils of the armature. We call that I squared R loss or copper loss. And so then if we take all those into account, we get the output power of the generator. So, oh, I forgot to write that. That's I squared R loss. So those are the mechanisms of loss that we have to take into account. Typically, stray, friction, and core losses are specified on a three-phase basis. Typically, I squared R loss has to be calculated from the armature current and the armature resistance. And then typically P out is given to you or can be calculated from known quantities. This also needs to be on a three-phase basis. So let's use that knowledge to solve this problem. We were told, or I guess we can summarize this. We can say that P out is equal to, well, let's start over here. The input power has to be equal to the sum of all the other ones. So that's going to be equal to P out plus Pi squared R plus P core plus P friction and windage plus P stray. So that accounts for all the power losses inside of the generator. And so we were asked to determine the efficiency, and efficiency is going to be basically equal to P out over P in times 100%. So I need to determine P out and P in here. So P out for the system was given because we know it's delivering rated current and rated voltage. So P out is going to be equal to Vt times Ia times the cosine of phi. So that's going to be 236.8 volts times 60 times the cosine. Well, that's cosine of phi is just the power factor, so it's going to be 0.8. But remember, I need to do this on a three-phase basis, so I'm just going to throw the number 3 out front right there to account for that. And that's going to give me 34.1 kilowatts as my total output power three-phase. I was told that P stray plus P friction and windage is equal to 1.5 kW, and P core is equal to 1.0 kW. The total copper loss, Pi squared R, is going to be equal to the magnitude of the armature current squared times the armature resistance, and then I need to multiply that by 3 because it happens in all three phases of the generator. So in this case, it's going to be 3 times 60 squared times 0 because we assumed an ideal generator. So in this particular instance, there's 0 watts of copper loss right there. So I can determine the input power necessary to power this generator at this load just by adding all these up. That's going to be 34.1 plus 1.5 plus 1 is going to be equal to, well, let me write all that down, 34.1 kilowatts plus 1.5 kilowatts plus 1 kilowatt. So that's 34, 35, 36.6 kilowatts as the input power required to deliver 34.1 kilowatts to the load. The efficiency of the systems then just from this equation right here, 34.1 over 36.6 times 100% is going to give me an efficiency of 93.2% for this generator. So that's part A. Part B was asking us to determine what's the applied shaft torque and what's the induced counter torque by the armature reaction. So this is in applied torque by the prime mover, this is induced counter torque. So I'll start at the output, T, that's this one again, T induced times omega m is equal to P converted. And if we go back to that figure, since I squared R loss is 0, P converted is equal to P out in this example. So is equal to P out. So I can determine the induced torque by the armature reaction by dividing the output power by the angular rate of rotation of the prime mover. And we knew this was a 60 hertz generator, so the angular rate of rotation is going to be 2 pi times n over 60. And n is going to be equal to 120 F over P. So that's 120. I believe this was a 50 hertz generator. Example 3.18. Don't have it. Oh wait, did I write it down up here? I did not. Gonna pause the video for a second. Check that frequency. So yes, this was a 50 hertz system. So 50 hertz goes into the signal there, and the number of poles on the generator were 6. So that means this is a 1000 RPM generator, and the angular frequency is therefore 104.7 radians per second. And so the induced counter torque by the armature reaction is going to be P out, which was 34.1 kilowatts, divided by 104.7 rads per second, and that's going to be 325.7 newton meters. And then the applied torque from the prime mover is going to be P in divided by the angular rate of rotation. So that's just going to be that 36.6 kW over 104.7 equals 349.6 newton meters. So there might be some small confusion where those numbers came from. Remember, 60 hertz is the electrical frequency. Electrical frequency is set by the rate of rotation in the prime mover, which is what is spinning the rotor. And since the rotor and the armature field are in synchronism, they spin at the same rate. So the angular speed of the armature magnetic field is the same.